In 2006, in Vancouver, Canada, a frustrated Mozilla programmer named Graydon Hoare climbed 21 flights of stairs, not because he wanted to, but because his apartment building's elevator had crashed. Again, and not from mechanical failure, but from software, bad code, a bug. That moment of frustration would change the world of software forever. Do you remember your 2006? Kaizen Royale was on a screen, Feather was created and launched publicly that would influence later platforms. Apple transitioned Mac computers to Intel processors. Everybody was using Mac OS X Tiger and Windows XP. The Elder Scrolls 4 Oblivion was running on PC and Xbox 360. And back to the broken elevator. He wasn't just annoyed, he was angry, and he thought, we computer people, we couldn't make even elevator that works without crashing. That's ridiculous. And then it hits him. If bad code could strand people in a broken elevator, what else was breaking? What other systems, critical systems, were crashing because programmers couldn't manage the memory correctly? Showtime. Look at this very simple C++ app. It doesn't crash, but it destroys logic quite badly. This app controls a microcontroller, and microcontroller controls a pump that pumping oil into a tanker ship that carries oil. Pump can be controlled via 3 commands: 0 exit, 1 disconnect, 2 connect, and it's sent from a console. When it happens, when a pump is connected, it runs the command pump oil, and when it's disconnected, stop pumping in oil. It's pretty logic, but there is an issue. You can pause the video, maybe you can spot the issue. First of all, we need to compile up, and now we are ready. Run the main, we can exit PS0, works. Now let's run it. First of all, I want to connect, and I am expecting that when I connect it start pumping oil. Connected, but it stop pumping oil. What? The initial command is pump oil, then the next command is stop pumping, but the current command must be a pump oil, but it's stop pumping. But more disastrous event can happen when I disconnect a pump. When I disconnect it, it starts pumping an oil, and it's totally disaster. Basically, you're spilling an oil inside of a port, or maybe on top of the tanker. Why did that happen? It happens because we're borrowing here, and basically we're creating a pointer on the value here in the next command. And inside this if, we just set the next command to stop pumping and running a current command. And that's very dangerous. Yes, we can switch these lines. For example, we can move it here and run the next, but potentially it's really hard to spot even in this a couple of lines of code. But can you imagine if you have 1,000 lines of code? What if you have millions lines of code? It's insanely difficult. If you have structures, classes, it's very difficult to spot the error. Wait for the second part when I implement exactly the same app in Rust, and it will not compile. Graydon knew the problem. The industry's fastest language, C and C++, were memory time bombs. Developers had absolute power over memory, but that power came with absolute responsibility. One mistake, a buffer overflows, a dangling pointer, a use after free error, and boom! System crashed, security breach, real consequences, money lost. Microsoft would later discover that 70% of their security vulnerabilities came from memory bugs in C and C++ code. 70%! Not the logic, not the algorithm, just memory management. Just think about it. Memory management. Look at the table. It's impossible to be good in all 3 categories in the same time. But the question became, what if there is a third way? What if you could have the speed of C++ and the safety of Python? Graydon didn't know it yet, but he was about to create language that would be voted most loved programming language for 8 years straight. He started coding in his free time, 2006, quietly, no fanfare, just a guy in his frustration writing a compiler in a language called OCaml. That's quite good in it. He was obsessed with an idea. What if memory safety wasn't a choice? What if the compiler itself could enforce it? What if certain bugs simply couldn't compile? His Philosophy was radical. Technology from the past came to save the future from itself. For 3 years, barely anyone at Mozilla knew about it. The project had no name, no direction, and certainly no future. Graydon worked alone, drawing inspiration from languages most programmers had forgotten about. Clue from 1974, Erlang from 1987, and Limbo from 1996. And if you learn solid principles, one of them is the Barbara Liskov principle. And Barbara Liskov, she's the designer and inventor of the Clue programming language. In 2009, a small group of people at Mozilla finally discovered what Graydon had been building. And they got interested. Really interested. Then, in 2010, at Mozilla's annual summit, Graydon casually stood up and announced, "I have been writing a compiled, concurrent, safe systems programming language for the past 4.5 years. A small group of people in Mozilla got interested in it this past year, and we do not know exactly what will come out of it." What Graydon had built was a borrow checker. And it's genius. It's absolutely genius. Here's the idea. Every variable has exactly one owner. When you pass that variable to another function, ownership transfers. And before your code even runs, the compiler checks, is this memory still valid? Could this crash? Is there a data race? If yes, it won't compile. No runtime garbage collector slowing you down. No manual memory management. Just compile time and forced safety. And look here. It's the same code that controls the pump in C++, but written in Rust. And now you can understand probably the guys who are writing a code in Rust for microcontrollers. Look here, it's exactly the same. I tried to simplify it, but it's exactly the same. Basically the same logic. We don't have do while in Rust. We use a loop, and we're exiting a loop if it's 0. We just break. Here we can't compile because of that here. Next command, because it's borrowed. Cannot assign the next command because it's borrowed. Why and where it's borrowed? It's borrowed here. Let's run a compiler and see what does it say to us. And it says next command is assigned to here, but it was already borrowed. We can do that. We use the assignment operator here, but it's borrowed right here. And also it helps us to find the line 27. So it works perfectly. It prevents a disaster, and it tells us that our code is really bad. If I switch the place and put it here, it will not compile. You see, because it's borrowed. Yes, sometimes it can be pain in the ass, but it prevents those horrible errors with the pump. This is simplicity, but the borrow checker makes the difference. The compiler is your copilot, your second pair of eyes. It catches bugs before they happen. And this is revolutionary because you can't have a memory leak. Impossible. You can't have a use after free error. Can't happen. And you can't have a data race in multi-threaded code. Won't compile. But here's the twist. The borrow checker is hard to learn. Really hard. Developers who tried Rust got frustrated. The compiler fought them. It said no constantly. It felt like the compiler was broken, but it wasn't broken. It was saving them. The burden to have a good code is a picky compiler. Rust early years were chaos, constant breaking changes. The language kept evolving. Different versions weren't compatible. Developers would write code and 6 months later it wouldn't compile anymore. The team removed features constantly. Entire subsystem got ripped out. And 2013, they removed the garbage collector. And then they removed the pure functions, then type states. The language looked nothing like it was. And in 2013, something happened. Graydon Hoare stepped down. He'd spent 7 years building this version, and now he handed it to others. Nico Matsakis took over language design. Aaron Turan joined the core team. A governance structure emerged. An RFC process, request for comments for short, was established so the community could have a voice. By 2014, there were hundreds of passionate developers working on Rust, but the language was still unstable, still experimental. Most companies wouldn't touch it. The question hung in the air: would Rust ever be production ready? Or was it just a research project that would fade away like Clue, Modular, and many more others? And then, on May 15th, 2015, it happened. Rust 1.0 was released, and with it came a promise, a sacred promise. From this point forward, the Rust team announced, breaking changes are out of scope. The compiler will stay stable. Your code will work. That was a magic moment. That was when Rust became real. The compiler had 1,400 contributors. There were already 5,000 third-party libraries. The package manager Cargo was elegant as hell and beloved. The tooling, Rust FMT for formatting, Clippy for linting, were world-class. But adoption was still slow. Rust was still hard. The learning curve was steep. Most programmers looked at it and said, no thanks, C++ is fine, Java is fine, Python is fine, Golang is fine. For 5 years, Rust grew quietly. 2015 to 2020, good language, small community, respected but not mainstream. I first encountered Rust in 2016 at a security conference, when I saw a simple web page with a slogan: Rust is a system programming language that runs blazingly fast, prevents sigvaults, and guarantees threat safety. Those days, everyone on the conference compares Rust with Swift, and in late 2018, the Rust website was updated and the slogan was changed to empowering everyone to build reliable and efficient software. And after 2 years empowering the brains of the developers with a new slogan, came the catalyst. In 2020, the Linux kernel started considering Rust not just as an experiment, as an actual language for core kernel code. Security researchers had studied it. The Linux community took it seriously. In December 2022, a historic moment, Rust became the first language other than C and assembly to be supported in the Linux kernel. Think about it. The most critical software on Earth, billions of servers, trillions of lines of code, and they choose Rust. Then the dominoes fell. Microsoft started rewriting Windows libraries in Rust, Google rewriting Android, Amazon rewrote part of AWS. Every major tech company realized the same thing: Rust was the answer. In February 2021, the Rust Foundation was created. 5 founding members: Amazon, Google, Huawei, Microsoft, and Mozilla. They committed $20,000 USD grants, full-time maintainers, and serious resources. From one programmer's frustration with a broken elevator, Rust has become the language that the world's most demanding systems are built with. It's not the easiest language. The borrow checker will make you angry. It will feel impossible at first. But that feeling, that's not the language being broken. The compiler refusing to let you write the broken code. And that's the whole point. And I want to end this video with a slogan said by Rust's creator, Graydon Hoare: technology from the past come to save the future from itself. The elevator works now. See ya.